Hello friends, this video on DNF block elements part 31 is brought to you by examfear.com. No more fear from exam. So what are F block elements? F block elements are called inner transition elements, and in these block all the elements, the last electron enters F orbital. So you see, the last electron enters F orbital. That is the definition. And they are all part of group 3. Actually, group 3 member, it is all extended from group 3. If you see, 57, it starts from here, 58, 89, it starts from 90. So these are actually my F block elements, lanthanides and actinides. Okay, so 14 elements in lanthanides and 14 in actinides. Total 28 elements. F block, 2 series, lanthanide series and actinide series. Lanthanus actually is not a lanthanide, but it resembles the property of lanthanide. So actually we study lanthanus also in this. Same thing, actinium also is not part of this actinide series, but it resembles the property of actinides. We'll also study actinium with actinides. Okay, all these lanthanides, they resembles one another, and these have only one stable oxidation state. We'll see that all these lanthanides have only one stable oxidation state. Actinides, we'll see that they have wide range of oxidation state. This is something you will see, wide range of oxidation state. So please remember, lanthanides, you will see that it has only one oxidation state, and actinide will have wide range of oxidation state. So before going further, let's at least see this element and say hello to them. So we'll start with the first lanthanides element called cerium. Cerium, atomic number 58, you can see here. And this is also silvery, soft, ductile metal, easily oxidized to air. This is named after the planet Ceres. And this is generally found in the minerals, monazite, basterite, and this is added to fuel actually to reduce the emission. This is added to fuel and it reduces the emission. So if we talk about the electronic configuration of cerium 58, we'll see that it is 4f1 5d1 6s2. This is the electronic configuration of cerium. Okay, and if you talk about, let's suppose, cerium 2+, in that case electrons will come from this place, right? And if you talk about cerium 3+, electrons will come from this place. If you talk about cerium 4+, electron will also come from this place. Okay, the next element is praseodymium. So in this case, this is also soft, silvery, malleable, ductile. This is magnetic, and this has electrical and chemical. It also has optical properties. This is also found in combined form, and this develops oxide layer. We have seen most of the D block also develops oxide layer. This also develops oxide coating due to oxidation, and this is named for the color of its oxide. This came from the Greek word called prasinos, and this prasinos means green, right? And the other word is didymus. This came from praseodymium, praseo plus didymus, and didymus means twin, because its oxides were green color, so it is called praseodymium. Okay, it has one stable and a lot of radioactive isotopes. Talk about electronic configuration, this 4f3 6s2. That is the electronic configuration of this element. Okay, and then we have neodymium. Neodymium, again, this word again came from the Greek word. Neo means new, you must know that, neo, and didymus means twin. Didymus means twin. This is again a silvery metal which tarnish in air. This forms oxide, but in this case this oxide layer actually is peeled off. So here no protective coating like iron. it doesn't form a protective coatings. Since the layer which forms, it peels off like iron, so it is further exposed for oxidation. Okay, it is present in the ores like monazite. It is not found naturally. It is used in glass dyes and to make powerful magnets. It is actually a rare metal. Okay, there are 5 stable isotopes and pretty good number of radioactive isotopes. We talk about the electronic configuration. It is 4F46S2. This is the electronic configuration of this. The next is promethium. Promethium, all radioactive isotopes only. It doesn't have any non-radioactive isotope. All radioactive isotope it has, and it was discovered in 1945 by analysis of fission product of uranium fuel. And this is named after this word Prometheus. This is a Greek word, Prometheus. Right? This is a Greek titan in Greek mythology who stole the fire from the Mount Olympus and bring it down to the human. So this actually shows the human intellect, because this is a human who created this. So it shows at that time it showed the power of human intellect. And this Prometheus also was very intellectual. He brought fire from the Mount Olympus down to human, and so it was named after him, and it's called Promethium. To talk about the electronic configuration, it is 4F56S2. This is the electronic configuration of Promethium. The next is Samarium. The Samarium is silvery hard. It readily oxidizes. It was discovered pretty late 1879, and this was named after the Samarskite ore actually, which was from which it was isolated. So this is the 40th most abundant metal in the earth. This is not rare. This is not rare, and this is used to create powerful magnets. And this is helpful in curing cancer. Okay. Talk about electronic configuration 4F6S2. This is the electronic configuration of Samarium. The next element is Europium. This is the first element which is named after a country, Europium. This is again hard, ductile, silvery metal. It also readily oxidizes in air. And this is used in lasers and fluorescent lamp. Okay, let's talk about electronic configuration 4F76S2. This is the electronic configuration of Europium. Gadolinium, this is again silvery white, malleable, ductile, detected in 1880, and this was named after gadolinite. What is this? This is the ore from which it is found. We have 6 stable isotopes and 1 radioactive isotopes also. It is used for shielding. It is used for shielding in nuclear reactor. Nuclear reactor we have. This is used for shielding the nuclear reactor. Shielding nuclear reactor. Okay. It is also used to prepare alloys which are resistant to high temperature. Talk about electronic configuration 4F7 3D1 6S2. This is the electronic configuration. The next element, terbium. This is also silvery white rare earth metal. This is malleable, ductile and hard, and this is also used in fluorescent lamps, TV tubes, sonar system, etc. This was discovered in 1843. This was named after a village, Yttrium. You must have heard this word. A lot of elements were found here, and this is in Sweden. This is named after the village Yttrium. Right? Talk about the electronic configuration 4F9 6S2. This is the electronic configuration of Yttrium. So next to terbium we have Dysprosium. This Dysprosium also, if you see, the silver white soft metal discovered in 1886, named after the Greek word dyspriotos. That means hard to get. This element was hard to get actually. It took time to prepare this, and it is used in making control rods in nuclear reactors. It has high magnetic strength, but it tarnishes slowly because it gets oxidized in air. Right? 4F10 6S2. This is the electronic configuration of this element. Next element is holmium. So we talk about holmium. This is again soft, malleable, again silvery white metal discovered in 1878. You see all these metals were discovered in the same time, and this is named after the city Stockholm. Holmium, Stockholm. This has the highest magnetic strength of any element. It is used in nuclear reactor. A good way to remember, Stockholm attract a lot of people. Similarly, this holmium is very attractive. It has very high magnetic strength. 4f11 6s2 is the electronic configuration for this metal. The next is Erbium. Erbium is again silvery white metal, solid metal, discovered in 1843, and this was also discovered in this Ytterby village in Sweden. This is used in photographic filter and also control rods in the nuclear reactors. 4f12 6s2 is the electronic configuration for this element. The next is thulium. Thulium is again, if you see, is again silvery white soft metal. It reacts with water and air. Also, it was also discovered at the same time, 1879. This was named after a place called Thule in Scandinavia. Right? This is used as X-ray source. This is used as X-ray source. 4f13 6s2 is the electronic configuration for this element. The next is YB, yttrium. This is soft white metal, malleable and ductile. This is the last second element of this lanthanide series, named after again the same village, Ytterby village in Sweden, where it was formed. And this is a source of gamma rays, right? And this is used for making atomic clock. Most stable atomic clock in the world is made using yttrium. Electronic configuration is 4f14 6s2 is the electronic configuration for this element. Next is lutetium. Lutetium is again silvery white. It resistant to corrosion in dry, but in the moist it actually reacts. And it was found in 1907, and the word came from the Latin word lutetia. Lutetia is the Latin word for Paris. And this is used as catalyst in the petroleum cracking. Catalyst in petroleum cracking. You'll see that not much application for the lanthanides and actinides actually. And 4f14 5d1 6s2, this is the electronic configuration from lutetium. So if you see the electronic configuration, the f orbitals has element ranging from 1 to 14. F orbitals are filled, right? The number of electrons are from 1 to 14. And S is typically filled. 6s2 is common for all. So for this lanthanoids, 4f1 to 14 6s2, I can say is the electronic configuration for this. D also has element, but D generally has 0 to 1 at the max. Okay, so let's talk about the trend in the atomic size for lanthanides. And we know that if you go from left to right, the atomic size increase because we are adding electron to 4f orbitals as we go from left to right, and 4f orbital has a poor shielding effect, and thus if you see the atomic size is decreasing as we are going from left to right, the atomic size is decreasing. This is my atomic size, and this value is decreasing. Correct? And this is called lanthanide contraction, and we know the consequence of lanthanide contraction. We already have studied this. Now we'll talk about the oxidation states. So in lanthanides, +3 is the most prominent oxidation state. +2 and +4 is also seen. +2 and +4, but +3 is the most common oxidation state. We'll talk about the general characteristics. We have seen that we have actually seen all these lanthanide elements. We have seen that they are all silvery white soft metals, and they tarnish rapidly in air, right? And their hardness increase with increasing atomic number. So in this direction, the hardness increase. Okay, the melting point is also high. Melting point is between 1000 to 1200 Kelvin. That is the melting point. They are all good conductor, good conductor. And this plus 3 ions are colored actually. Some of the plus 3 ions are colored, and this is because of F electrons. And most of them are paramagnetic. Okay, so paramagnetic is maximum for neodymium, and the first ionization energy is around 600 kilojoule and second ionization energy is around 1200 kilojoule, but the third ionization energy is low. And the chemical property of this lanthanide is similar to calcium initially, and then it becomes similar to iron, I think. Sorry, it is aluminium. So earlier lanthanums reacts like calcium, but if you increase the atomic number, these behaves like aluminium. Okay, and these actinides are highly radioactive. Sorry, I was a little confused here. The lanthanides actually, we have stable isotopes of lanthanides also, but in actinide we'll see that all these are radioactive, right? In lanthanides, we have elements which are non-radioactive also. In fact, I just explained to you that promethium is the only lanthanide which has only radioactive isotopes. Other has stable isotopes also. Promethium is the only odd man out which doesn't have any stable isotope, but other has stable isotopes also. Okay. The next is the chemical property. If you talk about the chemical property, lanthanum, when you react with nitrogen, it forms LNN. When it reacts with carbon, it forms LNC2 or LN3C or LN2C3. This kind of component forms. Lanthanum also reacts with the water to form LNOH3 kind of compound. Lanthanum also reacts with halide to form LNX3 kind of compound. Lanthanum also reacts with acid to form hydrogen gas. Lanthanum also reacts with oxygen to form the oxide, sometimes oxide coating or just oxide. Talk about the uses, not much use, but yeah, it is used in production of steel. It is used to create mesh metals, very hard metal, mesh metal. And this has 95% lanthanide actually and 5% iron. And this is used to produce bullets. Okay, this is lanthanum is also used for catalyst cracking. We have discussed this, catalyst in petroleum cracking. And this lanthanum is also used for television screen, the old television CRT screen. In that case, lanthanum is used for phosphor. It is also used for nuclear rod. Lanthanum is also used for nuclear rod. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.